Welcome to the kinematics of rigid body motion. Today we are going to discuss the Coriolis effect. Previously we determined that equation 486 is the basic kinematic law on which the dynamical equations for rigid body motion are founded. It is also applicable to a particle or system of particles moving relative to a rotating coordinate frame. For the latter, of particular importance is the description of particle motion relative to a coordinate frame rotating with the Earth. Inertial reference frames have thus been defined as frames of reference where Newton's laws hold. A system of axes fixed to the Earth is usually a good enough approximation in this regard. But an even better system is the one in which the local stars are fixed. There are observable effects arising from Earth's rotation relative to fixed stars. 486 provides the modifications needed for the equations of motion relative to the non-inertial system fixed in the rotating Earth. To begin with, let us consider the most general situation, which is that of a coordinate system rotating non-uniformly. Our basic kinematic law is the one here, and if we apply it to a position vector, the straightforward result is this one, giving the connection between the time derivatives of the vector and the laboratory and rotating frame. And we can consider applying it a second time, which amounts to bringing this operator once again onto the result here. And what we obtain is this length expression, which, if we multiply it by the particle mass, can be written in a generalized form of Newton's second law. So we obtain that mass times the acceleration in the rotating frame is the applied force, which is just the mass multiplying the acceleration in the laboratory frame minus this collection of terms, which we will analyze them in greater detail a bit later. But specifically now, what we want to show is the following. Namely, if in this expression so keep in mind the coordinate system rotates non-uniformly, so its instantaneous angular velocity changes with time. But we want the particle under study, we would want it to be perfectly at rest in the rotating frame, so it has no velocity and no acceleration in the rotating frame. And furthermore, we want the axis of rotation to be perpendicular to the radius vector of the particle. And then if we put all of these things together, we find a familiar expression for the applied force, which has a centripetal component, which is just this is the reverse of the centrifugal effect experienced by the particle, and a normal component, which gives its tangential acceleration. So in effect, what we're seeing here is the force applied in the case of a particle undergoing accelerated circular motion. Now we will perform a very similar analysis, but considering that the rotation is uniform. So we apply the operator 486 to the radius vector of a particle to obtain the expression here, and then we apply it once again with this restriction of the rotation being uniform in order to find the slightly more compact expression here. And once again, if we multiply it with the mass, we can identify the left-hand side as the applied force in Newton's second law. And then if we shift terms around a bit, we can cast things in this form. And furthermore, if now we identify the right-hand side with the effective force as seen in the rotating frame, the result is that this effective force is equal with the applied force, from which we must subtract these two terms. The first is the Coriolis term, and the second one is just the centrifugal term. And as a very basic application of this important result, consider the situation of a wagon wheel which is rotating about a vertical axis with angular frequency omega, and having a bug which crawls on one of its spokes with constant velocity with v0 and having a coefficient of friction mu. Then the radial velocity of the bug is the one here, and the angular velocity of the wheel is this one. And then if we apply the result we just obtained, considering that in this case there is no applied force on the bug in a Newtonian sense, then the total effective force in the rotating frame is immediately given by the Coriolis term and the centrifugal term. Now, the frictious force is simply the one here, and in order for this analysis to make sense, we will assume that we can neglect the Coriolis effects on the bug, in the sense that we will assume that given the ratio here, this term is given this ratio being much smaller than 1, so the bug moving at a small velocity compared to the overall rotation of the wheel, the Coriolis term is much smaller than the centrifugal one. Then we ask the question, at what radius would the frictious force become equal with the total effective force given by the centrifugal acceleration? And the result is simply the one given here, and it corresponds to the distance at which the bug can crawl, starting from the origin of the rotating frame. And at this point, since the two forces are equal, what happens is that beyond this, the centrifugal acceleration overcomes the frictious force, and the bug begins to slide along the radial direction. In the case of Earth's rotation relative to the fixed stars, the instantaneous angular velocity is numerically given by the result here. So it is quite small, and as you can see, it comes from the product of two factors. The first one is the angular velocity relative to the radius vector of the Sun, and the second factor here is the ratio between sidereal to solar days in 1 year, and is the correction required to give the angular velocity relative to fixed stars. Taking r as the Earth's equatorial radius, the maximum centripetal acceleration becomes omega squared times r, which is the number here, or 0.3% of the standard gravitational acceleration. So this is a small but not entirely negligible quantity. The measured terrestrial gravity is a combination of the gravitational field generated from the mass distribution of the planet and the effects of the centripetal acceleration. These two give what is known as Earth's gravity field, which is opposed to the pure gravitational field. Furthermore, the centripetal acceleration tends to flatten the rotating Earth. A fluid planet would deform into the shape of an ellipsoid given by the equipotential surface of the combined gravity field. Outside of local variations in wind and tide, the mean level of the seas follows the shape of this ellipsoid, defining the so-called geoid. Aside of local perturbations, gravity is normal to the surface of the geoid and defines the local vertical. For phenomena occurring in the vicinity of a particular spot on Earth, The centripetal acceleration in equation 491 can be considered as contained in the vector g, which will be oriented along the local vertical. Accordingly, the magnitude of g varies with the latitude, being about 0.53% smaller at the equator compared to the poles due to the centripetal acceleration and flattening. The centrifugal force acting on a particle due to Earth's revolution around the Sun is appreciable compared to gravity, but is almost exactly balanced by the gravitational attraction of the Sun. Looking at the Earth-Sun system from a frame of reference rotating with the Earth, it is the balance between the centrifugal effect and the gravitational attraction that keeps the Earth, along with everything on it and Sun, separated. In a Newtonian frame, the picture is different, as we have seen in section 3.3. There, the angular momentum contributes to the effective potential energy to keep the Earth in orbit. The Coriolis effect on a moving particle is perpendicular both to the angular velocity of the rotating frame and the velocity of the particle. And it leads in the northern hemisphere to a deflection to the right of its direction of travel due to the angular velocity pointing out of the ground, and to the left in the southern hemisphere. At the equator, the Coriolis effect vanishes due to the angular velocity being horizontal. Its magnitude relative to a given particle velocity v is of the order expressed here. So again, it's a fairly small effect for usual velocities. And as an example, we can consider the case of a projectile that is fired horizontally along Earth's surface in the northern hemisphere. So the velocity is going to be parallel to Earth's surface, and then the Coriolis acceleration is given by the cross product here, where locally the angular velocity of the Earth decomposes accordingly, depending on the colatitude of that of the particular point where we are carrying out the investigation. So this is just a standard colatitude angle from spherical polar coordinates. And then if we put these things together and calculate the acceleration, it is approximately given by the expression here, approximately because we are neglecting the vertical component that would follow from this cross product. The idea being that the local vertical component is going to be very, very small compared to the local component of gravity, or gravitation, and as such we can neglect it. So if this is the acceleration vector, then its magnitude is given by the expression here, which can be integrated immediately to lead to the law of motion here for the y-axis, and meanwhile the law of motion for the x-axis is the one given here. As such, the tangent of the deflection angle phi is given by the ratio, and it's the expression here. And then if we are assuming that phi is a very small angle, we can once again carry out this approximation and obtain the formula here. So its time derivative is this one, and as you can see, phi varies uniformly in time, and the exact amount depends on the colatitude. The Coriolis effect is important in oceanographic and meteorological phenomena involving the displacement of masses of matter over large distances, as for example the trade winds or the Gulf Stream. Generally, advanced hydrodynamic models treat these problems to full extent. We can, however, consider the large-scale horizontal wind circulation in a simplified picture. All things being equal, masses of air move according to the pressure gradient flow, so from large pressure to small pressure. On the vertical, the pressure gradient is balanced out by gravity, leaving only horizontal persistent long-range movement of masses. This is what is understood to us as the wind. Pressure gradient forces are modest, comparable in magnitude to Coriolis effects. Without Coriolis effects, wind directions would be perpendicular to isobars. Due to Coriolis effects, however, winds are deflected until they run parallel to isobars, at which point the Coriolis effect opposes the pressure gradient force and ideally balances it out. This is known as the geostrophic wind, a cyclonic flow around the center of low pressure. At altitudes beneath several kilometers, friction effects and eddy viscosity keep the equilibrium wind from reaching isobaric parallel. We can now consider the problem of a particle that is cast along the vertical from the surface of the Earth in the northern hemisphere with the initial velocity v0. So in this case, the vertical acceleration is just the effect of Earth's gravitation, and therefore the integrating this once leads to the equation of motion here, and integrating again leads to the well-known law of motion that we are familiar with. Now we are interested, so we are launching from the surface of the Earth with this original initial velocity, and we are interested to find out what the maximum height is. So the maximum height will be reached when the vertical velocity becomes 0. So when we put this condition, the corresponding time is the value here, and then if we put this in the law of motion, we find the maximum height reached by the particle to be zeta equal with the expression here. Now we want to write down the Coriolis acceleration experienced by the particle while it was moving vertically. So its velocity is given here. The general expression of the Coriolis acceleration is this one, and once again the angular velocity of the Earth decomposes as shown here for these local coordinates. And as such, if we put everything together, once again neglecting any vertical components, the Coriolis acceleration is given by this expression. So the x component of the acceleration is this one. It depends on the particle's velocity on the z-axis, which we already know from here. So if we put them together, we find this expression of the acceleration in the x direction, and by integrating it, we end up with the general law of motion here. Now, when t is equal with tau, so when the particle goes to rest on the vertical motion, we will have the total movement on the x-axis is the distance xi or chi given by the expression here, and the corresponding velocity on the x-axis is going to be the one here. Now, once the particle goes to rest, it will begin to fall back down towards the Earth from its maximum height. So once again, if we start from the acceleration experienced by it being just due to gravity, we can find the law of motion on the z-axis, which is now the expression here. So starting from the initial height, it falls according to this law, and now we want to find the time at which the particle has returned to the surface, which obviously follows from this from imposing this condition in the law here, and we find the result T prime. And we want to study the Coriolis deflection during this phase of the particle's motion. So once again, this is the velocity, this is the Coriolis deflection, and this is how the Earth's angular velocity decomposes. And if we put them all together, we find this expression of the acceleration, which we can once again integrate using our as initial conditions the final conditions of the first segment of the motion when the particle was ascending, and we will find the law of motion here. So if we now put the t prime value of the time, so the value at which the particle has returned to the surface, and we use the result 1, we obtain the final expression of the total deflection along the x-axis for a particle that was launched in Earth's atmosphere and then came falling back down, to be the expression here in terms of known constants. So notice that it does not actually depend on the initial velocity of the particle. It only depends on the maximum height it reached. Now, if the particle simply fell directly from the height zeta, then what we have to do is use results 3 together with these conditions set to 0 in order to obtain the expression here. So notice that in this particular case, the deflection is 4 times less, and it is in an opposite sense with respect to the initial circumstances. Furthermore, if we were to study this, let's say at the equator, so where theta is equal to pi over 2, and we take zeta to be, let's say, 100 meters, then we obtain a total deflection of about 2.2 centimeters. And this is an experiment which is surprisingly difficult to perform, as the deflection can be masked by wind currents, viscosity, and other forms of disturbing influences. An experiment that is easier to perform and has more readily observable effects is that of Foucault's pendulum. And we begin from the general form of Newton's second law for a rotating frame of reference, and we will consider that the system under study in a rotating frame is a simple pendulum. So where the total applied force is the tension in the pendulum spring and the effect of gravity. So then the restoring force, which keeps the pendulum oscillating, is of the magnitude given here, where this is just the angle of deflection of the pendulum from the local vertical. And we for convenience, we're going to consider that the small angle approximations is true here, which would make sense because in practice this is a very, very large pendulum, and as such in this expression we can multiply and divide by the length of the pendulum, and then we can identify the ratio here with the square frequency of oscillations. And as such, from these two expressions, the total applied force, the total restoring force, can be written as here. Now, the cross product between these, so there needs to be an arrow here. The cross product between the angular velocity of the Earth and the velocity of the moving pendulum can be expanded as shown here, and again neglecting vertical components due to their small values compared with the gravitational acceleration, we find the expansion here. And now if we put the results 1 and 2 together, we obtain Newton's second law in the rotating frame of the Earth as shown here. And now the idea is that we would like to transform to a new reference frame rotating with a different frequency, which is omega prime. And we simply apply the procedure once again. So the mass times the acceleration in this new prime frame is going to be the initial force. So the initial effective force becomes our applied force in these circumstances, and from it we must subtract a new Coriolis term and a new centrifugal term. And if we now write the effective force accordingly to what we have obtained here, we obtain this lengthy result. And notice that in particular, if we choose omega prime to have this expression, then this term and this term cancel out, and the equation of motion reduces to that of a simple harmonic oscillator in 2 dimensions. Now, omega, which is the angular frequency of the Earth, is 2 pi divided by a day. So the conclusion here is that the plane of oscillation rotates clockwise by 2 pi times cos theta per day. And the conclusion is that at the North Pole, the plane rotates fully once per day for an observer on Earth. So the plane in which the pendulum oscillates. It turns out that Coriolis effects are relevant not only for classical physics but also for quantum phenomena. And as a first example, consider the case of polyatomic molecules, which can rotate as a rigid body while the atoms vibrate around their equilibrium positions. Due to these vibrations, the atoms are moving relatively to the coordinate frame of the rotating molecule. The Coriolis term then causes the atoms to move perpendicularly to the original oscillations. Perturbations in molecular spectra due to Coriolis effects thus appear as interactions between the rotational and vibrational motions of the molecule. Furthermore, it is useful now to remember that for a point mass, the force due to the Coriolis acceleration is the one given here. And it is important to observe that this can be cast in the form of the gradient of a generalized potential, where this generalized potential function is identified with the dot product here, where omega is the angular velocity of the rotating frame and capital L is the angular momentum of the particle. When written like this, it is clear that the Coriolis force tends to divert the motion of the particle in a plane which is normal to the rotating frame's angular velocity. The implication of the second form is that a particle moving in a rotating frame has the lowest Coriolis energy when its angular momentum and that of the rotating system are aligned. This is known as rotational alignment, and it is discussed in a short article in the American Journal of Physics given here, and this discussion is the basis for the presentation that follows. And what is said there is that in deformed rotating atomic nuclei having odd mass, so a total number of protons and neutrons which is odd, The low energy states can be described as the odd particle rotating around an even mass core. Even mass meaning that a core has an even total number of protons and neutrons. The Coriolis potential U can dominate the energy spectrum either for large angular momentum of the odd particle or large core rotational velocities. In order for U to be minimized, the single particle motion will be such that the particle and core angular momentum are maximally aligned. In this situation, the motion of the odd particle is essentially decoupled from that of the core, a phenomenon which is observed by the close similarity between the energy spectrum of an even mass core and that of the rotational line states in the odd mass neighbor. The odd particle has a minimal influence on the relative excitation of the total system. And what is fascinating is that if we return to classical physics, there is an analogous phenomenon to nuclear rotational alignment, and it can be seen in Jupiter's atmospheric dynamics. The Jovian atmosphere is segregated into definite parallel bands of material which move in orbits whose angular momenta are aligned with the planet's rotational velocity vector. Jupiter's rotational velocity is more than twice that of the Earth, so Jovian Coriolis effects are more pronounced than their terrestrial counterparts. Vertical convection currents on the planet are Coriolis diverted into horizontal trajectories that encircle the planet in rotational aligned orbits. These jet streams are the extreme versions of Earth's less pronounced trade winds. The discrete nature of Jupiter's bands is due to the stability induced against longitudinal deflection by the Coriolis force. In conclusion, we have discussed Newton's second law of motion in a rotating frame and have studied its additional terms through simple examples. We have analyzed the Coriolis effects due to Earth's rotation relative to the fixed stars for a variety of situations, such as the deflection of a particle moving parallel with the planet's surface, the formation of cyclones, the deflection of a particle moving vertically, or the Foucault's pendulum. We have seen that Coriolis effects appear in quantum systems as well, such as molecules or atomic nuclei. We have also discovered that the physics applied in the case of the Coriolis effect in atomic nuclei is conceptually the same as the one behind the dynamics in Jupiter's atmosphere. In the following, we will discuss the rigid body equations of motion. With all that being said, I thought it would be interesting to close this chapter with one of the recent images of Jupiter as was taken by the James Webb Space Telescope, and you can find the source of the image in the video's description. And there's a lot of beautiful physics to be seen here. There is a lot of electrodynamics, of course, in the auroras of Jupiter and in the diffraction rings caused by the presence of its satellites. One can also see the thin rings orbiting Jupiter. And regarding the previous discussion, one can clearly see the Coriolis aligned bands of material which form the well-known granulations of its atmosphere. And of course there are other complex phenomena taking place here as seen in Jupiter storms, the most famous one being the red eye here. So, with all that being said, I will let you admire the image, and I will catch you later. Goodbye.